the electron is spinning in clockwise, the same direction to the directions of gravity of an arrow of the clock, clockwise direction. And this in the orbital we present by using, it is shown by using an arrow pointing upward. Positive half is shown by an arrow that is pointing up. So it may be half arrow like this, or it may be a full arrow like this, depends on the reference pole. That is fine quantum number. So it has two notations. So either half arrow pointing up or the full arrow like that one. Number 2. When the spine quantum number takes the value of negative a half, then it means that it means that the electron is spinning, electrons is spinning anti-clockwise direction, clockwise direction, anti-clockwise direction. This anti-clockwise direction in chemistry, notate it by using an arrow. We show it by using an arrow pointing down. So it is shown by an arrow pointing downward. It will be a half arrow, which is like this, or a full arrow like this, but is pointing downward. So it may be half arrow, or it may be a full arrow like that one. So it is shown by an arrow pointing downward like that. Okay, so simply that's the meaning. So since electrons exist in pairs, it's always denoted by this one and not the net magnetic field. The value of the spinning quantum number does not depend on any of the 3 quantum numbers. And this was proposed by the Goody-Smith and Lembeck to explain the double line structure of alkaline metal spectra. So since electrons exist in pair, so please start the full stop and say that since electrons existing in pairs, so since electrons exist in pairs, so we say that then the spine quantum number is, or spine quantum number is always denoted by plus or minus a half. Plus or minus a half. So what does it mean? This means that, for example, I told you, for example, for hydrogen, which is containing only 1 electrons, you know its atomic number is 1, atomic mass is 1. So this one, it is only 1 s orbital, because remember that. Let's say that n is equal to 1. So its principal subsidiary quantum number is equal to 0. Its magnetic quantum number is equal to 1, but its value for its magnetic quantum number is equal to what? Is equal to 0. So its finding quantum number for this case, if it is full of electrons, it is plus or minus a half. Okay, so suppose that this is just a certain element, let's say element X, this is the atomic number, this is the atomic mass. So it means that when you have an orbital, because I told the orbital we present by using the square bracket, so for positive a half, for example, we will be using this notation. So this means that this is positive a half spine quantum number. Or positive a half, if in the orbital we have an arrow, a full arrow pointing up, this also is equal to positive a half. So again, in terms of the orbitals, the negative a half we present by using the downward arrow. So this is equal to negative a half. Or if we have a full arrow, which is directed down, so use boxes, this also means that negative a half. In terms of finding quantum number. So then, in case you have any question about the spine quantum number, you can ask in the comment section. But according to the syllabus, that's what I have even taught you more than what the syllabus recommended me to teach you, because I know that sometimes questions challenge or comes in form of challenging and ask the students to think outside the box. So in case you have any questions, please use the comment sections, ask your questions about the spine quantum number, but that's what you have to know about the quantum number. So now, I would like just to teach you the last part, which is applications of quantum number. Applications of quantum numbers. And these applications of quantum numbers will have very relevant. I'll be teaching you 3 intensive applications of quantum number. And then we'll be doing examples now. Applications of quantum number in general. Because I taught you applications of quantum number separately. It means for the principal quantum number, applications of subsidiary quantum number. So now we want to say that we can have to teach about the applications of quantum numbers in general, all the 4 quantum numbers. The first application is this. So we say that quantum numbers, all the 4 quantum numbers are used in physics and chemistry, are used in determination. These are used in determination of maximum number of what? Of electrons. Definitions of maximum number of electrons at the shell may accommodate. So quantum numbers, the first application said that the quantum numbers are used in determination to determine what? To determine the maximum number of electrons that the shell may accommodate. Right? Determine the maximum, not the minimum, the maximum number of electrons that the shell may accommodate. The shell of what? Of an atom. We say that an atom contains what? Nucleus and the shells. The electrons are always found in the shells. And the whole study of hydrogen spectrums and the quantum numbers deals about the shell of an atom. So within the shell of an atom, we have the principal quantum number, we have subsidiary quantum number, we have magnetic quantum number, we have spin quantum number. But the primary intention is to determine the maximum number of electrons that the shell may accommodate. Means if it reaches its maximum capacity, then the electrons will not be accommodated. Very interesting, very important subject in atomic structure. So then now, I would like just to clarify this concept by using some of the examples. Okay, by using some of the examples. So this is, I don't remember the number for example, but this is the example. Let's say example 1 for this case, or example 2, example 3. But the question states like this one: by using quantum numbers, using quantum numbers, deduce total number of electrons. In the first shell. The first shell of an atom. In any first shell. Because every atom has a first shell. Hydrogens have a first shell. Helium has a first shell. Neons has a first shell. Magnesium has a first shell. Copper has a first shell. Zinc has a first shell. So the question is determine the maximum or deduce the number of electrons, the total number of electrons in the first shell of an atom by using the quantum number, or quantum numbers, all the 4 quantum numbers. So solution, it's a simplest question, because always when God helped me to prepare a session or a lecture or a period, and then it's the time for the problem solving, I always examine all the questions and start from the simplest, going to the intermediate difficulty and going to the complex or difficulty examples, because at that level, now you have the fundament. First of all, you won't be afraid that this concept is complicated, I cannot afford it. And then you understand that even the real life problems, we have always to start solving simplest problem. We get encouragement, we got the intermediate level of the problems, and then got the complex problems. You can't get into complex problems if you cannot solve a simplest problem. So this is the simplest problem, remember that. Okay, so we say that by using quantum number, so you can write the number of the examples. I can call just for the quantum number, I can call even example 5, because I gave you some homeworks. So regardless, you can write the number the way you like. So by using the quantum numbers, deduce the total number of electrons in the first shell. Okay, so we're using the table method. Okay, we're using the table method where we have 2 columns and several maybe rows. So let me solve the problem here. So solution. So let me start with, because how many quantum numbers do you have in chemistry or in atom? 4. Principal quantum number, subsidiary quantum number, or angular momentum, or azimuthal quantum number, or what? We call it subsidiary quantum number, and hence you have magnetic quantum number and spin quantum number. So let us start with the first one. The principal quantum number. Principal quantum number. So the principal quantum number, this is represented by using which letter? N. So what will be the principal quantum number for the first shell? Is equal to 1. Right? It's equal to 1. So let us have a column here. Let's have a row. So the principal quantum number, the value of principal quantum number for the first shell is what? Is 1. Then we go for the second. So second we have subsidiary quantum number. The subsidiary quantum number, and this subsidiary quantum number, in an atom we have the letter L. How do we find the letter L? I told you that L is equal to, or starting from 0, then increasing, the maximum value is n minus 1. So what the value of n? 1. So 1 minus 1 is what? 0. So the value of L for this case is what? Is 0. Again, remember that the principal quantum number does not tell us the total number of electrons. The subsidiary quantum number does not tell us the total number of what? For electrons. What information do we get here? This is the first shell and the first, or the energy level, that or ground state. Electrons is mostly they like to remain in this energy level. And then so what information do we get here? We get that when L is equal to 0, means this indicating that this S sub energy level. So we got the third quantum number, which we call the magnetic quantum number. So magnetic quantum number. So the symbol for magnetic quantum number, it is M. Its formula, to know that value, we have two formulas, because it depends on what we are representing. We have M is equal to 2L plus 1. So for this case, which will be equal to 1. But also we have MS, or M subscript of S. So M subscript of S, no, M1, sorry, excuse me, this is the M1. M1, we say that the general formula is from negative L, then you proceed to 0, then you proceed to positive L. So for this case, means that M1 is equal to, the value is 0, so 0. So M1 for this case is equal to 0. Then the first quantum number is spinning quantum number. So how many orbitals? Because when you have M is equal to 0, this is only one orbital. So the number of orbitals I know the number of orbitals by its magnetic quantum number. So because you have only one orbital, it means that the spin quantum number now, spin quantum number means that the orbital, it can accommodate only 2 electrons. That's the maximum capacity of one orbital. So the spin quantum number, which is ms or s. So for this case, because its values, we say that because can accommodate plus or minus a half. So its value will be plus or minus a half. Can accommodate 1 electrons oriented in clockwise, and other electrons that is in anti-clockwise direction. Then that's the end of that question. Interesting, yeah? Okay. So again, I would like just to go to another example. Teaching you applications of 40 of quantum numbers in general. So the second question now, you have to be careful now. It's just like building a tall building. So let's say if we've done this example 60. Okay, so deduce the maximum number. So for this case, it means the conclusion you say that the first shell can accommodate only 2 electrons. Reduce the maximum number or the total number of electrons. In some of the questions, they might ask you that to use what? To use, we call it the principle, to use the quantum number, but in some of them, they don't tell you what should you use. But for you, the best way is by using the quantum number. Good. Reduce the maximum number of electrons. Solution. Let me teach you how you can do this problem. You can solve this problem. So, the first one is always a principal quantum number, so which we call Tm. Right? Okay, for the second shell, for reduce the maximum number of electrons in the second shell. What the maximum number of electrons in the second shell, right? So n, that's 1, so we say that this is quantum number. And hence, this is the value of its quantum number. You have to be careful. So the first one is n. For the second shell, n is equal to 2. And then, what is, so n is equal to 2. So we say that here, the principal quantum number is n is equal to 2. Then you go for the second principal quantum number, for the second quantum number, which is the subsidiary quantum number. So for this case, because we say that we have n is equal to 2, we have 2 subsidiary quantum number. The first subsidiary quantum number is L is equal to 0 and L is equal to 1. And then we have magnetic quantum number, which we call M1. So M1 for this case, for 0 it will be only 0. Okay, for 0 it will be 0. So this is 0. For 1, we are going to have 3 magnetic quantum number. The first one, we have -1. Second, we have 0. Third, we have +1. That is magnetic quantum number. So then, satisfying quantum number, which is S, or called the M subscript of S. So for this one, we'll be having a similar diagram that we have there. We have to explain the total, the maximum. So the M0 will occupy plus or minus a half. And also, when magnetic quantum number is equal to -1, we occupy is a plus or minus a half. And also this one might occupy plus or minus a half. And also this one will occupy plus or minus a half. So if that's the case now, we can conclude that the maximum number maximum number of electrons that can be accommodated in the second shell is, so you see that 2 electrons plus 2 electrons plus 2 electrons plus 2 electrons, so it's 8 electrons. 8 electrons. So it's 8 electrons. And here we have S orbital and P orbital. So S orbital can accommodate only 2 electrons. P orbital can accommodate 60 electrons. S sub energy level can accommodate just only 1 orbital. It can accommodate only 2 electrons. This is P sub energy level. It has 3 orbitals, and each orbital accommodates 2 electrons. So 3 times 2 is 6 electrons. So its capacity, the P sub energy level, it can accommodate only 60 electrons. So in total, for the second shell, n is equal to 2. then the shell, it can accommodate only 80 electrons. Why it is 80 electrons? Because I told you that the spin quantum number will take the positive or the negative a half value in a particular orbit. Positive a half indicate that orientation is clockwise, and negative a half indicate that orientation is anti-clockwise or downward. So again, let me take you to the last example for this case, then I'll give you the homework for this application. The question asks you that use the maximum number of electrons which can be contained in the third shell of an atom. Reduce the maximum. These are common questions in the exam. Mock call, testing, midterm. Reduce the maximum number. Final exam, the way it is, it's not easy, but it's simple when you've been taught one. So reduce the maximum number of electrons that can be accommodated in the shell in the 30 the steady shell. The steady shell of an atom. So solution. So we'll be using the table. So we have a column of quantum number. You have to be careful for this case. Column of quantum number. And then so we're going to have another column for values. Values of 40 of quantum number. So listen carefully, because this is the last example for this application. Next I will give you the homework. And it will be a very interesting homework because it will test whether you have understood what I've been teaching or you are preparing yourself to cram. So the primary, always the first fundament, the first quantum number is principal quantum number. So if the question asks us about the third shell, it means that the value of principal quantum number is equal to 3. Listen carefully. Okay, so if you ignore, it will cost you. Then we have the next quantum number is called the subsidiary quantum number, which is L. So for this case, from the formula I told you in lecture 12, and even, yes, lecture 12, we say that this one, we may get it from the general formula, which is from 0 to n minus 1. So here, we are going to have, because n is equal to 3, we are going to have 3 values. So we have the first value, which is 0, and the second value, and the third value. So let me write like this, because the meaning of doing that. So here we have 0. So we have 0. And then here we have 1. And also subsidiary quantum number might be 2. Don't rush. When you are following these lectures or this session, don't rush. So then the next quantum number, we call it a magnetic quantum number. It's the lowercase m or lowercase m subscript of 1. So then for this case, here we are going to have 0. And then for this one, we are going to have 3 values. We're going to have negative 1, we're going to have 0, we're going to have positive 1. For this now, when L is equal to 2, we're going to have 5 values. 3, 4, like this. So then this is negative 2. This is negative 1. This is 0. This is positive 1. And this is positive 2. Then we have what? First principal quantum number, which is fine quantum number. So because we know now the top number of orbitals, because the functions of magnetic quantum number tell us the top number of orbitals, then it is easy. It's simple for us now to fill electrons. Because we know the top number of orbitals for that case. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 orbitals. So because you have 9 orbitals, still accommodates 18 electrons. So here we have what? We have plus, minus a half. 2 electrons. Again here we have a plus, minus a half. 2 electrons. So then we have plus, minus a half. 2 electrons. Then you have plus, minus a half. 2 electrons. Then you have plus, minus a half. 2 electrons. Then you have plus, minus a half. 2 electrons. Then you have plus, minus a half. 2 electrons. Then you have plus, minus a half. 2 electrons. Then you have plus, minus a half. 2 electrons. So total is 16 or 18. Because 9 times 2 is what? 18. 18 electrons. So we say that the third shell, therefore, the third shell of an atom can accommodate only 18 electrons. Testing. Parent testing. So now it's time for the homework in this application. It's time for you to test yourself whether you understood what I've been teaching you in this fantastic lecture. Okay. You can go through review, you can go textbooks, you can go different textbooks and then reviewing what and see how the questions being asked me on this part. So this is homework and this is homework 13. So what is the maximum number of electrons that can be accommodated in the shell with this principal quantum number n of A, n is equal to 5, B, n is equal to 4. If you manage to answer this question, then you are competent enough in the concepts of 40 of quantum number. So, if that's the case, let me teach you the second application of quantum number in general. We say that quantum number Quantum numbers are address. So these are the address of